There's no carbon NMR for the 2-nitrofluorinone. Yeah, so there's no interpretation of that carbon NMR. Other questions? Lab this week is the Wittig reaction. The Wittig reaction is in the white handout. Is that right? You have a white one? That's going to be covered on the syllabus. It says in lab lecture. Instead of doing it in a lab lecture, I decided to make a video for it. I posted that yesterday. That will only be covered by the video. We will be doing that lab this week. It is a group lab and a group report. It's also a choice of starting material for the aldehyde. We can perhaps on Wednesday assign our groups so that you can do SciFinder search. If you, I don't know if what the information says about size of groups, usually 3 to 4. If we're going to try to do it ahead of time, we need to have a group on Wednesday, and it'd be good to have a group name. Okay. We have, a purple sheet? Green? Purple is the alpha carbonyl chemistry. Green, I think we pretty much finished up. I do have your quizzes. Return. If you want to pick that up here, please yell. Section Thursday lab first. Lacey? Meredith? Laura? Mackenzie? Zaravi? Wayne? Here. Alex? Here. Esther? Here. Stefan? Here. Elizabeth? Here. Ananya? Here. Charles? Here. Friday lab. Ronak? Here. Donald? Here. Samir? Here. Jennifer? Here. Queen? Here. Margaret? Here. Victoria? Here. Porsche? Here. Sanjana? Nicholas? Here. Lawrence? Here. Grades range from 10 to 1.5. Board outside my door has a couple of these. You may have heard of the next Star Wars movie. It's called Star Wars Episode 8, The Last Fluorine. Fluorine teaches the Force to its 8 disciples to bring order back to the Force and restore peace, trust, and republic. Okay.
Only if they actually predicted the last.
I mentioned this one here. This nice one here. It's Casey and Sunshine Band, multi-step synthesis fluorine derivatives. Take a benzene, add a nitro, get down tonight. Get down tonight. I remember when I used to teach Georgia State, we did another type lab and it had 7 or 8 reactions, and one of my favorites, I reckon, one that I remember fondly was a student did it as a cookbook, and the first was an appetizer, and the appetizer was like the 2-nitrofluorine, analogous to us. And I remember one of them was the whatever beef stew. and it was a 7-course meal or something. It was nice and memorable. That was 20 years ago, or pushing 20 years. Okay. Alpha carbonyl chemistry. Enols, tautomerize. Is that right? When we did mechanism, Oreo, did we do acid or base catalyzed when we did it in class? Base?
Yeah.
Okay, we did base. We may have to do acid catalyzed on the next page. Which one of the following are enol tautomers are the one in the box?
The first two.
What's the definition of a tautomer? Relocation of one hydrogen. That's it. Nothing else moves. One hydrogen is relocated, and then pi bonds. One. It could be more than one. Yes, this is tautomer. This is tautomer. How do you recognize tautomer? Well, with carbonyls, enols. Okay, but it can be enol on either side, this side or this side. Those are not tautomers. They're also not enols. But a tautomer doesn't have to be an enol. They're not enols because the OH is not on the ene. And if you look at here, we've got an H here that ain't there. But we've also got an H there, right? And neither one of those H's was in the one in the box, so that means 2 H's have moved. That means it ain't a tautomer. Same thing for over there, right? So I think the answer is just the first 2 are tautomers. Is that right? How many enol tautomers possible for this compound?
4.
4? I'm not thinking 4 unless I missed one. You got them all 4 drawn? Who said 4?
Wouldn't it just be like the double bond on each side and then the 4 different like stereoisomers of it? I mean,
No, you're not going to have any stereoisomers of the alkenes here because of the green.
Well, that double bond doesn't like.
Do what?
No, never mind. I think
You
that's.
got them drawn?
I think I did it wrong. I kind of did like where the double bond moved up, and I think that's what I messed up.
Well, one that we could draw that's probably the most simple is just to draw the enol over here.
Yeah, that's where I messed up.
Yeah?
You can do one more as well.
Okay.
Put that 5 on the left and then the 5 on that side.
Other enols we could draw is, first off, we have to have an all for the enol. We can put the double bond here, and over here we can put double bond there. There you go. There's an enol tautomer of the compound. Which H has been relocated when we went to here? One there. Which H has been relocated when we went to this tautomer? Not that H. There's one H there. There's still one H here. Instead, we relocated this H, one of these H's. We can also draw this tautomer. Double bond there. Ultimately, a way to maybe look at this back over here is, what H's are acidic? Here, which H's are acidic here? You've got an acidic H there and acidic H here. Relatively acidic. It's really not considered an acid, but relatively acidic. More than the others, right? We can make anion here, conjugated, it would be resonance stabilized. We can make anion here, resonance stabilized, and that leads to both enol tautomers. Same thing here. This H is relatively acidic. This H is not. Draw an anion there. There's no resonance. The p orbital, the conjugation is already there with the pi bond. Not. But here it is. Because look at this anion. If you had that anion, can you draw resonance into the carbonyl? Yes. It's vinylogous. Alkene sometimes called vinyl. We can draw resonance. I'll do it all at once. Electrons here, electrons here, electrons here. That's going to give anion on the oxygen. It would be just anion here. Pi bond here, pi bond anion, and then you just pick up proton. There's your resonance, Oreo, off, resonance, put it back on here. Same thing over here is we can make anion here, boom, boom, and you put double bond here, boom, and then in the end, H's, alpha H's, okay? But if we have a pi bond, that's alpha, these H's, that H is actually not acidic, but here it is. This H is essentially an alpha H via the double bond, because we can make anion here, and then we can do resonance. Okay, the same thing I did there. And so the acidic H's are here and here. The double bond just connects the carbonyl with the anion, as opposed to just being right next door. Okay? I think the answer is 3. Somebody said 4. I think it's 3 for enols. How many additional CH tautomers are possible? Because an enol is an OH tautomer. Well, we could draw how about that there? If I showed you that, is that a CH tautomer of the original? Yes, we just relocated one of these H's. 3 there, only 2 here. One of them is now here. 1 there, now 2 here. And the pi bond has been moved. This is just where if we had done resonance, instead of moving the anion all the way to the oxygen, we just move it to the carbon, and then the carbanion picks up a proton. But we could also have done the same thing over here. That there, and that there. Those are both CH tautomers, yeah? Is there another one? Again, the H you're going to relocate is acidic. That's acidic because of resonance into the carbonyl. We can relocate it here. But that one is 2. But here, if we relocate this, you can only relocate it to the oxygen. And that would be an OH tautomer, not a CH tautomer. Okay, you should look at that, work through it. We don't have time to keep at it right there. Basically, the double bond there gives additional tautomers. Okay, understanding that. Alpha substitution reactions. Halogenation. Very common. Looks a little odd at first. We can take this methyl ketone here, acetophenone, right? We can brominate it, elemental bromine, acid catalyst, and we can do an alpha bromination. Very common to be able to do halogenation at the alpha position. We can do it either under acidic or basic conditions. Here we're under acidic conditions. And the reactive species is the enol. This with the H plus catalyst is converted to the enol. I'll just do phenyl. Now on the previous page we did this mechanism for the tautomerization, but I was told we did it basic catalyzed. Let's do this acid catalyzed. It's the same thing, Oreo, but what's the first step? Proton on. We've got H plus. Proton on where? Protonate carbonyl. Protonate carbonyl. What's next? Resonance. Is there any resonance of this?
Yes.
Well, it's just one pi bond, that's it. But we can move the pi bond up onto oxygen. The oxygen is electronegative. It does want to pull the electrons. And by moving it up, we delocalize the charge onto the carbon. Double-headed resonance arrow, right? Of course, this is major resonance structure, more bonds. But this is resonance, right? Just a different Lewis structure. All we did is move pi electrons. We moved them with our dipole, helping us see the electron movement direction. Resonance, what's next?
Bromine or active.
Take proton off. What proton do you want to take off?
The right.
Which one needs to be taken off? There's 3 here, there's only 2 here. One of those needs to be taken off. Well, what's the acid? Let's say we use HBr and there's Br minus here. Br minus, then take this H, and these electrons just fall in here to make pi bond. And what does that give? That gives your enol. There you go. There's your tautomerization mechanism. On, resonance, off. Because under acidic conditions, you put protons on first. So the catalyst really is helping just form enol. Now, how's this equilibrium? Which one's favored at equilibrium? The carbonyl is. Okay? And so this equilibrium is really like this. But that's okay. There's a little bit of this here. Now with this here, this is just organic 1 chemistry. Because at this point we have an alkene. That becomes the predominant thing. And do alkenes react with bromine?
Yes.
You did that reaction organic 1. That was one of the first reactions we looked at. It's the alkene that's really reacting with bromine. Okay? Schizophrenic, partial polarization, alkene. We're going to leave cation if this alkene attacks bromine, right or left?
Right.
It's going to be left. That there, this gets kicked off. This is just alkene chemistry. That leads to bromine there, OH here, cation here. What would we do next in organic 1? This is cation really formed. Remember those questions? What do we do next? Particularly my guys, because other people may have did it a little bit differently. Back bond. Back bond, didn't we? This back bonding, and we said that's really not formed because the back bonding occurred at the same exact time. And the first intermediate is the bromonium ion. Here a little bit different. Because there's other electrons that can back bond. Are there any other electrons that can help this carbon out? No. Electrons from oxygen here. What if these come in? That is really not back bonding. What is this really?
Pi bond.
This is resonance because we're making a pi bond. We're just moving pi electrons. Resonance. And what does that give? Not quite yet. We have positive here bromine here, what do we need to do to get the final product? Something needs to take the H. What can take the H?
Water.
Right here. This we created plus Br minus, right? When the other bromine got kicked off. This can take the H. Leave electrons behind. Thus, the other product that's formed here is what? HBr. That's the fate of the other bromine. And we lose an H. This is going to produce HBr. We produce HBr. You may have used a 1 molecule of HBr as catalyst, but you're actually going to produce an equivalent of HBr. That's new HBr. That's not catalyst being reformed. Back over here is really where the catalyst worked. The catalyst does what? The catalyst helps get you the enol. From there, there's no need for a catalyst. Okay? The enol will react. The catalyst just speeds up the reaction by speeding up the conversion of the keto form to the enol form.
If your condition is under HBr, wouldn't it protonate the ketone again, and then couldn't bromine come and add on a second time?
Good question. We'll be getting to that. Typically, under acidic conditions, you can monohalogenate. And the second one becomes a little bit more difficult. Not sure I'm going to take the time to go into why. Under basic conditions, we'll talk about that more. Down below is an example with a ring. Typically, you like to not mix your halogens, though I reckon you theoretically could. I don't think you're going to theoretically worry about brominating if you use HBr, because HBr is not going to be an electrophilic source of Br. But typically, you want to keep your halogens similar. And so this is an alpha chlorination. In both of the examples we've done here, you're only halogenating on one side. Well, because the other side, there is no tautomerization possible, there's no enol possible, there's no acidic CH possible over there. Here, it's symmetrical, so it doesn't matter which side you do, you just get chlorine. If we did it over here, it'd be the same product, and we're only doing mono. Now, theoretically, you could maybe do chlorinate over here and get a dichloro, one on each side, but that would require two equivalents of chlorine, and you would produce two HCl. This reaction is actually known to be autocatalytic. It catalyzes itself. How can a reaction catalyze itself? Because you can actually do this reaction with no catalyst. Okay? What's going on here? What is autocatalytic? How is it autocatalytic?
Water.
This reaction actually starts out a little slow, but it's known to increase in rate as it goes along. Why? How? Because what?
You form HCl.
Yes, because you're making ACl as a byproduct. And what does ACl then do? It then turns around and starts catalyzing it. So you're producing the catalyst. It's called autocatalytic. It starts out slow and then it speeds up for some reason. It's because you're generating ACl. The ACl is helping convert this to the enol. It's speeding up the tautomerization of this to the enol. And the enol is what reacts with the chlorine, because it's the ene. And it's just alkene chemistry with an OH there. We didn't clarify back up there, why do we make carbocation next to the OH? Because it's present and stabilized. And it wasn't back bonding in this case. In this case, it was just resonance. Because resonance is always there. Resonance is not a step, right? As soon as something's formed, it's resonance stabilized. And because it's resonance stabilized, there's no need for back binding and making that strained bromonium ion. And so it's known to not form here, and you just end up, from the resonance structure, you just end up with your carbonyl back. Under basic conditions, you can also halogenate, but typically you have to do exhaustive halogenation. Take this ethyl ketone, excess chlorine, excess hydroxide, and we're going to dichlorinate. We have two acidic H's, both replaced with chlorine. Mechanism here. You could say similar thing. You could say, well, maybe this is converted to the enol, and the enol reacts with chlorine. And you say the hydroxide is just acting to catalyze the tautomerization. But actually, it's not enol. It's actually enolate. Well, the enolate is more reactive, and it is formed. So let's propose that the more reactive enolate is going to be halogenating. Hydroxide takes the H, leaves us behind. We can move towards the enol, doing Oreo, proton off. What's next? Resonance. Then you can put proton back on and you can get enol. But instead of doing all that, we're good to go right here. Because the enolate anion, now I've got this, we can show resonance of this and put the anion here, but it's reacting on carbon. And right here you have a nucleophile. And this can just chlorinate. Those electrons attack chlorine. And so it's the enolate. On the previous page with that mechanism, did we ever form enolate anion? No. Previous page is the enol. Because an alkene, a neutral alkene, will react as a nucleophile. Here, though, we have a carbanion, the enolate. We don't have to go to the enol. And what does this give? Gives that. If we complete all that, what else have we formed here? We formed H2O. That was where the base took the H. What else did we form here?
NaCl.
If we balance this all out, sodium chloride, right? Will we balance that? How do we get another chlorine there? Repeat the process. Just repeat the process. We still have another acidic H. Under basic conditions, it's very hard to monohalogenate. Reaction does not stop here, okay? It's hard to stop here. That kind of implies that it's easier to halogenate this than the original. Why might that be? The answer lies in the acidity of the CH. Which CH is more acidic? The original one or this one? Well, let's show the resulting anions. Remember in organic 1, when we judged acidity, what do we look at?
Conjugate
Stability
base.
of the...
Conjugate base.
Yes, let's look at the conjugate base. This anion versus over there. Here's the two enolates. Which one's more stable? Why is this one, Donald?
The chlorine?
What about the chlorine?
Wasn't it?
I didn't hear that. Sound like you said resonance. No, there's no resonance. You're not going to draw. This is an anion. You don't. If that was a cation, we could do resonance. How do you stabilize an anion? You don't move electrons towards an anion. Yeah, and there's no resonance. You can't draw anything there. What's the answer here? The chlorine's doing what? It's just electronegativity. Okay? Electronegativity, the inductive withdrawal of the chlorine makes this, that's more acidic than that. So, when this reaction is taking place, the hydroxide is like, ooh, an H. But once that starts forming, what does the hydroxide do? Ooh, hey, come over here, I'm going to take this H because that's an easier H to take. And so instead of, you can't say hydroxide or whatever, I want you to only react here, it won't listen to you. It's going to start reacting over there, and you're just going to dihalogenate before you even monohalogenate. If you try to just monohalogenate, you're going to end up with like 50-50, a mix. So under basic conditions, you typically have to just go all the way to the end if you want to get a pure product. And in this case, 2. If this was just if it was a CH3 here, you would be doing a trihalogenation. Question?
So would it be different if we didn't do excess at all? Or
If you don't use excess, you're going to get a mixture of mono, di, tri. And so the way to get a single product is just to shoot for tri if that's exhausted. In this case, exhausted was dichlorination because there was 2 acidic H's. Under acidic conditions, you can monohalogenate. Under basic conditions, exhausted. Okay? Show product below. And the hydroxide here is not catalyst. Hydroxide's consumed. Just look at the first one. Did we, when we monochlorinated, did we reform hydroxide? No. We made water. Okay? So it's not catalyst here. So you got to use a full amount of hydroxide. How's that look? Don't forget the other side. Up here, there's no acidic CH on the other side. Here, there's 3 acidic CHs. We're going to halogenate each one. Deprotonate, brominate, deprotonate, brominate, deprotonate, brominate. Yeah? A bit of a theoretical question to consider. What if we treated this with bromine and H, or acetic acid, or HBr, basically acidic conditions? What are we going to make here?
monobromation.
And I can clarify this. Typically, unless it's shown, this is one equivalent. Okay, I can clarify that by showing one equivalent. What are we going to get here?
Brominate on the methyl. With more substituted alkene intermediate.
Very good. Tell me again.
We would brominate on the methyl because there's a more substituted alkene intermediate.
Yeah, but what do you mean brominate on the methyl?
Next to the methyl.
Next to the methyl. You have option here. Yes. There's some deeper considerations here, this advanced chemistry. The thing that I will look at here is, if you consider the two different enols, because down here, what's the reactive species?
You know,
Not the enolate, but the
you know,
enol. There's no enolate form down here. You don't form carbanions under acidic conditions. It's the enol. And the question is, there's two different enols, and the answer for, there's deeper discussion here, but one of the things to look at is which enol is more preferred. And Nick, which enol is more preferred?
Left side.
This enol is more preferred because it's an alkene and it's more substituted. It's more thermodynamically favored. And so that's one argument to why this would be the product. There's other arguments here that I'm not going to get into that sort of cloud the discussion and are beyond us. It's more difficult. Basic conditions, try halogenation. Don't forget the other side, okay? Haloform reaction. It's a neat reaction that involves this chemistry. We take a methyl ketone. Did it say methyl ketone? Methyl ketone, treat it with X2. This is X typically halogen, Br2, Cl2, most common. I2 is also possible. Excess halogenation. I mean, that's just what we did above. And then an acid workup. I mean, excess chlorine and hydroxide. Excess chlorine and hydroxide. That's going to give, I'll just say X. How many X's on this carbon? 3. And a lot of times this is shown like this. I actually show the carbon. Like a CCl3 or a CBr3. That's exhaustive halogenation, putting 3 halogens there. Exhaustive halogenation. But that ain't the product. How do we get a carboxylic acid instead? We're not working this up yet. At this point, we can get additional chemistry. We have hydroxide. Everybody agree? There it is. Excess hydroxide. This can add to carbonyl. Electrons up. You guys have to be careful here. When I drew this, some of you guys know mechanisms are drawing things like this. You're not connecting the bond to the right atom of your group here, okay? This is just a little bit lack of attention to detail. This needs to be the O is bonded to the carbon and then the H, yeah? But here, what can happen next? Electrons back down, and the CX3 group can actually be kicked off. CX3 could be a leading group for acid derivative chemistry. Addition, elimination, what does this give? Reformed carbonyl, there's an OH there. And what did we make? We made that carbanion. Can this be a leaving group? Well, we've always said anytime you can make a pi bond using a lone pair like this, kick off a leaving group is easy to do. And we said we'll see lots of things leave. And when I said that back over there in that other handout, I said, I mentioned haloform reaction. Well, here it is, haloform reaction. Why can this leave? And you're not going to kick off a CH3. But why are you able to kick off this CX3? Well, we just saw this on the previous. We got 3 halogens here withdrawing. This is a pretty stabilized carbanion. And this chemistry is known to occur. Now, this will take an H though. And this is going to give the O minus, right? Because if that doesn't take the H, then hydroxide, which we have excess of, would take the H. But when this takes an H, there's that. Okay? So this is in step 1. What's the purpose of the acid workup?
Put the proton down.
If you want to protonate this, you need to add your favorite acid. But this is in general called haloform. For example, if this was chlorine, CHCl3, a lot of times it's shown like this, you put the H on the other side of the carbon. But what's the name of this compound? Chloroform, yes. It's actually a common solvent in the lab. A little bit toxic. I don't like it. If those were bromines, it would be called bromoform. If it was iodine, it would be called iodoform. Everybody with me? If he's talking general, it's called
Haloform.
haloform. Okay, it's called a haloform reaction. Often you're not worried about this. This is going to end up in the waste container. What is this a synthesis of?
Carboxylic.
Another way to make carboxylic acids, but this, in this case, from a methyl ketone. And the first main part of the reaction is exhaustive halogenation. But then, this gets kicked off. The carbon will only get kicked off if there's 3 halogens on it. Above, we did the same thing. And that carbon did not get kicked off. It only has 2. Would you have ever been able to predict this? No. But this is what Mother Nature has given us. Carbon with 2 halogens will not get kicked off in this addition elimination chemistry, and you're just measuring. But if there's 3, it will. Imagine the first person who did this, I'm going to exhaustive halogenate my product today. And then my product has no halogen in it. How did this happen? My product is acidic. What is this? This is not what I expected. Oh no, this other chemistry took place. You did not expect it. Conversion of methyl ketones to carboxylic acid. This is also a chemical test called you use iodine here, iodoform test. It's a test for methyl ketones. Because if you do this with iodines, the reaction will occur, but if the X is iodine, that thing over there will be a solid. It's a solid. It's only a solid with iodine. With chlorine, it's a liquid, and it's used as a solid. With bromine, it's a liquid. With iodine, it's a solid. And under the conditions, the solid will precipitate. It's also a kind of an ugly yellow turbid solid. It's not very crystalline. It's kind of milky, like semi-solid. Typically, nothing else is going to be a solid here when the reaction works well. And so, if you get a yellow precipitate of the iodoform, you know that that could only have been formed if you had a methyl ketone in your original. And the solid is a positive result. Which one of these isomers would give a positive iodoform test?
The one on the right.
The one with the methyl ketone, right? Exhaustive halogenation, and then boop, that gets kicked off. Exhaustive halogenation here will just lead to diiodination. And that will not get kicked off. You will not generate iodoform there. You will not get a solid. So we have a chemical test to distinguish a methyl ketone from a non-methyl. Okay? See those constitutional isomers there? It's also possible for NMR. Useful because NMR, these two are going to be very similar. If you were just looking at the NMR, you might think, I'm not sure which this is. Maybe a chemical test would help me distinguish between the two beyond what NMR can do. Now, mass spec would actually be good for that. Mass spec could distinguish. If mass spec showed a prominent peak at M-29, which one is it?
Should have on
M-29?
the left. It's
That
big
would
map
be
and
the
echo.
right.
One on the
Left.
On the
one on
left.
the left. M-29, this would be M-15, both cases, because this would cleave here, and this is not going to give a benzylate. Okay, we don't cleave to give a cation on the ring. That's M-15 in both cases, that's M-29, and this might be M-H or M-1. But mass spec would be good. NMR, though, would be quite similar. So, of course, chemical test is just extra information, possible to distinguish between methyl ketones. Of course, both of these would give negative tolerance, right? What about DNP, 2,4-DNP? Would these give positive, negative 2,4-DNP tests? Two,4 DNP, both would be positive. Both would be positive. Because 2,4 DNP distinguishes what?
Aldehydes and ketones.
Aldehydes, ketones from other things like from esters. Yeah. Both would give positive 2,4 DNP. Both would give negative tolerance. With haloform, one gives positive, one gives negative. So chemical tests. By the way, there is a lab in the lab manual, the very last one. We're not doing it, but it's a kind of a chemical test lab. It might be useful just for review of your chemical tests. Chemical tests aren't really used quite as much as they used to be 50 years ago. But you'll still see them on some standardized tests, and it's still good chemistry, I think, to know. Okay, formation of. Take a look at this alpha halogenation. Why would we want to put a halogen next door?
Elimination.
Well, now you have a leaving group where you can do leaving group chemistry. Now you can do substitution, elimination. Okay, we'll be picking up here and moving ahead. Have a good day, guys.